If you have even the slightest interest in science, by now you've probably heard of an exciting new scientific facility called the Large Hadron Collider, or LHC. But what do you know about it? Well, first, the LHC is a particle accelerator. It is located at the CERN laboratory in Europe, just west of Geneva, Switzerland. This accelerator takes two beams, each containing about 300 trillion protons, and shoots them at one another. Even though there are lots of protons in the beams, individual collisions are only between two protons, one traveling in one direction and one traveling in the opposite direction. For the subatomic world, these protons have an enormous amount of energy, although from a human perspective it's really very small, about as much energy as a mosquito flying at full speed. However, this energy is concentrated into an incredibly small volume. The result is that when the protons collide, they experience temperatures of tens of trillions of degrees centigrade, which is over 100,000 times hotter than the center of the sun. In order to get a feel for what those conditions are like, we could ask, if we wanted to make a ball the size of a basketball with that energy density, how much energy are we talking about? The answer is simple. A lot. And I'm not kidding. It would take the energy of the sun itself. And I'm not talking about the energy of the sun hitting the earth. I'm talking about all of the energy of the sun. And not just for a second, a minute, a day, or a year. If you take the entire energy output of the entire sun for over 20 million years and concentrate that energy into the size of a basketball, that's what it's like in the center of an LHC collision. Studying matter under these incredible conditions allows us to learn what the universe was like a tenth of a trillionth of a second after the Big Bang, and to work out some of the most fundamental rules that govern the universe. And we've already had a big triumph. In July of 2012, we announced the discovery of the Higgs boson, which was the last missing piece of our current best theory of the laws that govern the universe. When the 2013 Nobel Prize in Physics was awarded to Peter Higgs and Francois Englert for the prediction of the Higgs boson, the entire scientific world basked in their glory. Of course, even with such a momentous discovery, we're not done. I mean, if you're in a mine and you find a huge nugget of gold, you don't stop. You keep digging. And LHC scientists are doing just that. After taking data from 2010 to late 2012, the LHC was temporarily shut down for refurbishments, retrofits, and upgrades. The spring of 2015 is the beginning of a new period of data taking that is expected to run for several years. Even better, the new and improved LHC is really that, new and improved. It will collide particles at over 150% the energy it did before, and with far more collisions per second. With these enhanced capabilities, scientists will look for all sorts of things, hoping for a discovery. You might ask, what are we going to find? But that's actually really a very silly question. After all, the LHC is a machine of discovery. To paraphrase a famous scientist, if we knew what we were going to find, it wouldn't be called research. But we do know what we're going to look for. We're going to look for supersymmetry, extra dimensions, precision tests of our existing theories, and deeper investigations into the properties of the Higgs boson, and maybe even make the dark matter that astronomers say is 5 times more prevalent than ordinary matter. And, of course, would be scouring the data looking for something entirely unexpected. That would be the coolest outcome we could hope for. There's another interesting aspect of the LHC. For those of you who might not have a scientific interest, but are fascinated by engineering, the LHC is an outrageous accomplishment. The LHC is a ring about 17 miles in circumference, about 27 kilometers. The beam travels around the ring about 10,000 times a second. To guide the beam in a circular path takes 9,600 magnets, of which 1,232 are especially strong. These magnets, called dipoles, use about 11,000 amperes of current to make a magnetic field 160,000 times stronger than the Earth's magnetic field. The energy stored in the magnets is 11 billion joules. That's enough energy to melt 15 tons of copper. When the beam is put in the accelerator, it circulates for a long time, say about 10 hours or so. During that time, the beam travels far enough to go to Pluto and back. In order to have a beam travel that far, the beam is kept inside a pipe that is under high vacuum. The vacuum is 10 times better than the surface of the moon. And the total volume of the beam pipe is about the same as one of Europe's majestic cathedrals. And if all those numbers weren't enough to blow your mind, the center of the magnets are cooled to incredible temperatures, to 1.9 Kelvin, or 456 degrees below 0 Fahrenheit. By any definition, the LHC is a spectacular scientific achievement. And the thing that makes the whole endeavor so incredibly exciting is that the experiments we do might discover something entirely new and change our entire understanding of the universe. We'd have to rewrite the textbooks, but you know, I am totally up for that. How about you?